Hi, my name is Owen Marshall, and I'm presenting work in collaboration with Kyung-Hyun Cho and Christina Savin at New York University. Now, in a neural circuit, there's a dynamic relationship between synapses and neurons, in that synapses determine the dynamics of the neural circuit, and neural activity in turn alters synaptic strength through plasticity rules. It's a core focus of computational neuroscience to try to reverse engineer what these synaptic plasticity rules are in the brain. And in other words, trying to understand how the dynamics of the circuit influence the learning of the circuit. But we wanted to ask the question from the opposite perspective, which is how does learning in the circuit, however it occurs, how does that affect the dynamics? And we want to ask this because if we could answer this question, it would help us reverse engineer what learning algorithm underlies synaptic plasticity. And that's because synapses are hard to measure at scale, but neurons can be measured at scale during behavior. So understanding a learning algorithm in terms of its effect on neurodynamics, rather than its effect on synapses directly, might be an ultimately more experimentally testable way to understand learning in neuroscience. So to study this, we use RNNs as a model, and we study the 3D flip-flop task from Brock and Cicillo, which is basically a task where the network has to report the most recent input in each of three independent dimensions. And some really beautiful work from Cosyne a few years ago, Maheswaranathan and Williams showed that there's actually really only one solution to this task in a dynamical system sense, and that is a lattice of 8 fixed points representing each of the 8 possible outcomes you could report in the network, with very precise input-driven transitions between those fixed points. Now, there's still an open question of how did we get to this cube? And this is true for any task, really. A learning algorithm may prescribe updates in the weight space, but that tells us nothing about how the dynamics themselves change. And there are a couple possibilities you could imagine a priori. Maybe the dynamics change in a very orderly way where there's an initial bifurcation into 2 fixed points, and then those bifurcate into 4. So then you have a square, and then maybe the square turns into a cube in this nice orderly fashion. Or maybe it's very chaotic and the changes kind of don't really make any sense. And a lot of the topologies, the network kind of stumbles in and out of partial solutions as it noisily converges on the correct topology by trial and error. So how do we investigate this? The idea is we're going to make full use of the fact that we're using an RNN, and we're going to checkpoint the learning process at different stages of learning and evaluate how the network is performing and what its dynamical system is at each point in learning. And there are many different analyses we could run, but we're going to focus on the topological characterization of the dynamics because that is sufficient for characterizing the network's function. And so we do that following the approach of Cicillo with some slight extensions, which is that we first search for fixed points of the network, and then we find the input-driven transitions between these fixed points. And then we compare how similar these transition probabilities are from checkpoint to checkpoint. And if we do this, we actually get a pretty rich story for a case of successful training by a biologically plausible learning algorithm, RFLO. As the network learns the task, the various geometric notions of distance change kind of in proportion to the magnitude of the errors. Early on, the network geometry is changing a lot, whether the synaptic strengths or the locations of these fixed points or the principal component axes all tend to change in proportion to how big the network errors are. You can think of this as neural drift, but the topological distance tells a rich story where early on in training, the network topology is totally trivial. Despite massive gradient norms, the network topology is just one fixed point. And then it enters a period of rapid changes where the topology starts changing very rapidly every single time step. And all of these very hard to interpret topologies that aren't necessarily functional. But then at some point, the network starts to finally converge on solutions, although it may lose them, before ultimately converging on a stable solution. So if you come by my poster, I can show you this narrative of the RNN's learning process in more detail, using movies, which actually can be a lot more illustrative than the static curation of a handful of checkpoints. Like they really don't do justice to, for example, just how rapidly the topology is changing every 10 time steps, even in the rapid changes period. And I can also show some preliminary work on how this whole set of learning stages might be altered in the case where instead of training the whole network at once, we train it in a sequence by showing it distinct input dimensions one at a time. Anyway, thanks for listening. Hope to see you there.